Hello everyone, I'll be explaining the solution to problem D1, Mocha and Diana easy version for Codeforces round 738. In this problem, you have two friends and both of them have some number of nodes, n nodes. And what both of them have done is they have created forests by adding edges between those n nodes. So both of them have different forests. I'll just show you what a forest is. For example, this thing is a forest. A forest is you can think of it as a collection of trees, and there are no cycles, and you can have one tree and you can have more than one tree as well. So what we are given is, let us consider the friends to be A and B, and both of them have n nodes and they have constructed forest having m1 edges and m2 edges. For example, if you have n as, let's say, 3, then one case of a forest is this. So this is a forest, you have 3 nodes and you have one edge only. And you can also have 3 nodes and you can have something like this. So you can have 2 edges. So the number of edges can be different. We want to find uh, that how many edges we can add between some vertices. So the vertices are labeled. For example, this is a forest having vertices 1, 2, 3, and vertex 1 might be somewhere here for the other forest. Vertex 2 might be here, vertex 3 might be here. So we have to choose pair of vertices and we have to add edges between them. For example, I can choose vertex 2 and 3 and I can try to add an edge like this. And similarly for this, I can try to add an edge like this. So correspondingly, if we have a vertex 2 here, then we will find the location of vertex 2 in the other forest, and similarly for the other node, and then we will have to add an edge between them. The condition is that whenever we add an edge, the structure should always be a forest. So the graph can basically never not have any cycles at any point. And you have to find what are the maximum number of edges that you can add. Okay. So I've drawn this figure. These squiggly boxes are basically a representation of a tree. So this is something like a tree. Okay. One more thing to understand here is that if you have got two trees and you add an edge between any two vertices in those two trees. So if I take this tree and if I take this tree, and if I add an edge between any two vertices. So for the first vertex should be in the first tree, the second should be in the other tree. So if I do something like this, the resultant structure will still be a forest. There is no way that there can be any cycles. But if I add a second edge, so if I've added a first edge between these two trees, if I add suppose a second edge like this, then there will be a cycle and it will not be a tree anymore. We can also add another edge like this, so it will still be a forest. Okay. Okay, so how do we solve the problem? I will first tell you the algorithm and then why it works. So the algorithm is that you will iterate over every pair of points u and v. So I iterate over all pair of points u and v, and if they belong to the same tree, if they're a part of the same tree, then you can not add an edge between them. But if they are parts of different trees, then you can add an edge between them. And once you add an edge between them, there will be some changes. For example, initially, in this case, in this example, these two trees were different. And if I were to pick, suppose, this vertex and this vertex, and I can add an edge between them, because as I said, it would still be a tree. Like, the combined structure would be a tree and we would still have a forest. But afterwards, then all of these edges this edge. Once you have added an edge, all of these and these are now part of the same tree. So this combined structure is a new tree. Basically, all of these are connected to each other. So you can use a DSU basically. If you add an edge between two trees, you can just join these two vertices together, and then with the help of DSUs, all of this node will also be joined with this node. So overall, all of them will be part of a single connected component. Okay, now back to the solution. Like I said, you iterate over all pair of points, and if they are in the same component, if they are part of the same tree, then you cannot add an edge between them. Otherwise, you can add an edge between them. So I'll try to show you an example. Suppose you pick 2 points U and V such that U is here, V is somewhere here in some other tree. But for B, U is here and V is also here. So with respect to A, these two are parts of different connected components. But with respect to B, they are part of the same connected component. So if you try to add an edge here, this green structure would have a cycle in it and B would basically no longer have a forest. So if either of them, for a pair of points U and V, if in either A or in B, they are in the same connected components, then you cannot add an edge between them. But if you have something like this, if you have, suppose you have got U here and V here as well, then you can, there is no issues, you can add an edge. Suppose we add this edge, we add an edge, and using DSUs, basically we have now joined these two different connected components into one single connected component. And similarly, for A as well. Now, the reason this is optimal is that in the future, if you suppose, in the future, suppose you had picked any two pair of points like these 2 points, U dash and V dash. And if the corresponding points were here, U dash and V dash and U dash. So the existence of this connected component and the existence of this connected component has no effect on whether we can add an edge between these two. So this is one of the possibilities. So we can simply add an edge here and we would still have an optimal answer. But suppose this is not the case. Suppose we have U dash here, V dash here, and we have V dash here and U dash we have somewhere here. Okay. So you can easily see that you can still add an edge here. You can still add an edge between these two components. You could still have added an edge between these two components. So like it will have no effects. It would always give the optimal answer. That's what I'm trying to say. So to summarize, maintain a DSU for both A and B, and initially when you're adding edges, you are given the initial forest. So just uh, modify the DSU using the given edges initially, and then iterate over all pair of points. If those pair of points belong to the same connected component in either A or in B, then you cannot add an edge between them. Otherwise, you can add an edge. I will also show my implementation. So this is a DSU class. You can join two nodes. You can find the parent. You can check if two nodes are in the same connected component. Then I made two DSUs for A and B, and since the first DSU had M1 edges, the second had M2 edges, so I took those edges, I joined them together. I said that okay, they're in the same connected component. Now in this loop, I iterate over over all pair of points. If they are in the same connected component for either A or B, then I cannot join them, so I just continue. Otherwise, I can add an edge, so I add that to my answer. I also push that edge to my vector, and I join those two nodes in both A and B. Thank you for watching. Bye.